some of you might have looked up what I and J are all about, but let me at least speak my piece about I and J, and then I'll return you to that warm up. Okay. So, did we talk about unit vectors yesterday? How how we might care in our lives about vectors that are 1 unit long, and it's easy to make them. There are 2 unit vectors of they're very simple and important, and those are the unit vectors in the x and the y direction. And they're so important to us that we give them these names, I and j. So I is the unit vector in the x direction, and j is the unit vector in the y direction. So they just have simply those components, right? They're the vectors that are 1 unit long in the x direction, in the positive x direction, and in the positive y direction, right? And the reason I think that this is worth mentioning, even though it seems so redundant, is that it begins the conversation about the following powerful idea. And that's that, like, taking 2 vectors, if I hand you 2 vectors, can you, using those vectors, construct every vector with those 2 vectors? And the answer for these is a pretty clear yes, right? Because using some multiple of I and some multiple of j, and kind of like mixing them together, you can produce any vector you like. Do you see that? So in some sense, like, I and j is the very, very small toolkit that allows you to do everything. Like, they're the only 2 vectors you need. You keep them in your back pocket, and then you have, like, with you every vector. You can produce any vector. And then the interesting follow-up question would be, are there other sets of vectors that would do that for you, like that you could take 2 of and produce every vector from? Play around with that idea. It's the beginnings of a concept called independence that you'll talk about in linear algebra a lot. So this follow-up question is not meant to be difficult then. Is it clear from what I mean by, like, if you have some vector, any vector, something comma something, that you can write this way in terms of the unit vectors? Knowing what we know about scalar multiplication and about vector addition. So this was our last slide from yesterday, and when you're ready, Cheyenne, maybe you can just tell us how we write this then here. It's not meant to be a trick question. Don't overthink it. Yeah, it's 53.2, comma, 127.8. You can just tell me.
Would it be 53.2 times 1 comma 0?
Yeah, which we have a name for.
Or I.
Right.
Plus 127.86.
Right, like I said, don't overthink this one. So yeah, I mean, it's not even worth asking really, maybe. And I know some of you might be thinking like, oh, this is just yet another way. We've exposed you to a couple ways now of like writing vectors and expressing them. So this is like just another quote unquote notation. Well, I want to make sure this is kind of saying something actually a little deeper. That like actually what you're looking at is, yeah, I mean, I guess you could consider it another way of writing vectors. That's true. But I also want you to consider it as like our vector being built from the basic vectors. And by I and j here, those are vectors, people, right? That's the vector I and the vector j, right? So I want to make sure you like understand what's going on there. It's actually speaking volumes about like building things from other things. Yeah. Those are the unit vectors in the x and in the y direction. Yeah. Everyone, even not in this classroom, will know what you mean when you talk about the vector I or the vector j. Yep. And then we'll actually add a third one called, what do you think we might call it? K, when we go to the z, when we need a z-axis. and that will be the unit vector in the z direction. So I, J, K, everyone will know what those vectors are. Sometimes in a physics class, you'll write them this way: I hat, J hat. I don't know why physicists like hats, but there you go. All right, back to your regularly scheduled warm-up now. Have we talked about bearing before? Maybe not. I don't know. So bearing is weird. It's not. It's like a real-world thing. Like we prefer as mathematicians to talk about angles and standard position. But in the real world, if we're trying to draw out what this tank is doing, the bearing of 161 degrees means measured clockwise from north. Okay? So north being north, right? Clockwise being this way, yeah? So if we're talking about 161 degrees from north, then we're really talking about like which quadrant did we land in? How about quadrant 4, right? So that's where our velocity vector is going to be drawn. Okay, so this is the vector will represent the tank. If you want language that we've used to express that, what angle would you probably call that? If this is 161 from north, measured clockwise, then what must this angle be here? 71, or we might call it negative 71 in standard position, or you could call it whatever the positive version of that is, you know. At 360. Good, and then again, we want to maybe consider it also like 27 miles per hour long, kind of, right? It's like 27 miles per hour long. Again, you can see why the word length here is not a helpful one. The magnitude of the vector is 27 miles per hour. I think I like that better, right? Or the speed is the way we say that. The magnitude of the velocity is speed is 27 miles per hour. Great. So that's a picture of what this tank is doing, kind of, right? That's its velocity, at least captured in a vector. And now it asks for the component form of its velocity, so let's actually see if we can figure out what that would be. How did we do this yesterday? This is just in the real world context, but we have the magnitude and we have the angle and standard position, then what is its component form? Using some trig, and we came up with this nice formula. Yeah.
27 cosine negative 71, comma, 27 sine negative 71.
Good, and then let's just approximate what that is. Oh, you have it already? 8.79, 25 point something. Can someone like give an amen on that? All right. Well, I didn't even have to reach for my calculator. You supplied the numbers. That was beautiful. Okay. So there's not. This is meant to be just kind of a little warm up. Number 2 comes the hard work, actually, maybe. But this is good. Let me interlude between numbers 1 and 2 the following discussion, which I think maybe some of you have had before. Have you had this discussion? So say you're in your family 16-passenger van, okay? And you're in the back. The van is going 40 miles an hour that way in a line. Yes, you're picturing the situation. You're having a great time listening to your favorite beats. You have a ball, you throw it to your brother, or maybe it's even maniacal. You're like throwing a ball at your brother or something. So if you throw it at, have you done this example before, right? If you throw it at like 15 miles per hour, the van is going 40 miles per hour. How fast does it go relative to the ground?
55.
Have you done this before? Right? Is that right? It goes 55 miles per hour with respect to the ground. It still hits your brother because he's moving at 40 miles per hour. It still hits him at 15 miles per hour, right? Relative to him and relative to you, it's moving 15 miles per hour. But if you were to look at it along the road, you know, or said another way, if you were like in the back of a truck and you would throw a ball off the truck, and assuming no air resistance, and it was going 40 miles an hour, and you would throw it at 15 miles per hour forward, it would be going, with respect to the ground, 55 miles per hour, yes? you want me to draw a picture? This is real. I promise this is all really good stuff. Okay.
You're just adding this to one thing to the
Okay, so all right, so this truck is going 40.
Why is he throwing it in the direction that the truck is gonna go?
He's trying to hit a bird.
Hey, he has free will, just like you do,
Why is he so large?
for the sake of the example. All right, so the ball relative to the truck, it's gonna depart from the truck at 15 miles per hour, right? Every hour it will be 15. I mean, if it didn't drop with gravity, but you with me. Okay, it would be traveling 15 miles per hour this way if the truck was motionless. Well, if we move the whole picture forward at 40 miles per hour, then with respect to the ground, the ball travels at 55 miles per hour. Is that the thing you've thought about or talked about before? What happens if he throws it backwards at 15 miles per hour? How fast would the ball be going? Huh? 25 miles per hour. Which direction would the ball be traveling actually with respect to the truck? It would actually be traveling forward with respect to the ground. It would actually be still traveling forward, right? With respect to the ground. Well, because the truck is moving 40 miles per hour, the ball is only moving 15 miles per hour, right? You should definitely think about this next time you're flying in a plane. I love thinking about this when I'm flying in a plane. Imagine throwing a ball, just how about you don't throw it at all? You just throw it straight up and have it come back down to your hand on the plane, right? Imagine doing that. To you it looks like just like, oh, isn't that fun? But if you were to have like a transparent plane, and I were to be able to see that from the ground, the path that that ball actually traveled from my perspective on the ground is like it just traveled like 60 feet, didn't it? Because the plane is going like 400 miles an hour. Right? So in that time, like it's actually moved from there to there in space, hasn't it? Next time you're in a plane, think about this. It'll keep you really quite entertained, okay? Or if you're walking down the aisle, you can be like, I'm going 403 miles per hour, you know? In the middle of the air, 40,000 feet in the air. Okay, so think about that. The reason I ask that is now I'd like you to consider this same example in the example of a tank, okay? So now let's say that we're in this tank and we're traveling according to this velocity vector right here, 27 miles per hour at this angle. So this makes this thing a little weird. And say you throw the ball 15 miles per hour from the tank, due east. Yes? That is directly in this direction, right? How fast does the ball go? Again, ignoring air resistance and things like that. How fast does the ball go? Well, 27 miles per hour is not what we're adding to the velocity, right? What would we be adding? How much velocity does it have in this direction? Well, it has 15 miles per hour worth of it because I gave it that. But how much did the tank give it in that direction? To be precise, 8.79, yes, is the amount of velocity that the ball is given by the tank in that direction, yes? So we can actually be quite precise in the answer to this question. It would be whatever 8.79 is plus 15 miles per hour is the amount of velocity it would have in that direction. You see why these components actually might have some meaning for us? That's the amount of velocity that's being contributed in both of those two directions, okay? So, I mean, what that means is, like, what if I were to throw the ball at some angle, right? Well, I just have to, like, resolve the two components, and I think what we've agreed is that we just add, right? It seems like in this situation, we just add the two vectors in the one-dimensional case. In the two-dimensional case, we maybe just add the components too, right? So that's going to be a guiding principle as we do number 2, because we have like two vectors we're dealing with. We have like an airplane and a wind, and the question that I want to know as the pilot, is this like wind going to help me along? Is it going to make me faster? Is it going to make me slower? And then maybe it's going to change my heading just a little bit too, right? Right. Okay. So let's draw these two pictures again. We're practicing thinking about bearing too. So let's draw these two vectors as reasonably as we can. We'll start with the plane. So what does it look like to have a bearing of 352 degrees from north, measured clockwise? What'd you say, Franklin? Is this your second one? Go ahead, Ian.
And that would give you 82 degrees total.
82 degrees in standard position, you mean?
Yes. In standard position, you'd be at 82
352 degrees?
plus 90.
So I'm thinking like from north, measured clockwise. So we're going around this way 352
Oh,
degrees,
measured
right?
clockwise.
Yeah, great. 98? Yeah, where does that look like here? It'd be like almost the whole way around, right? So we'd be like here then. Something like that? 352 degrees from north measured clockwise. Okay, so then now I'm ready to hear you say it again. What is that, Corinne? That's 98 degrees. Okay, I think I get you on that because it's like we're 8 degrees short of being there. And you're like in standard position, I would probably call that 98 degrees. I think I'm with you. 90 plus that 8. Yeah. Yeah, so this is 98 degrees. Is everyone with us, me and Corinne, on calling that 98 degrees from our own? I mean, that's the way we like to name it, isn't it? I think we would all agree. Like, my goal would be to like eliminate bearing from the problem as quickly as possible and like think about it in my own terms, you know. What's wrong, Franklin? Okay. Number 2, go. Yeah.
I actually have a question. The wind blowing at 300 degrees, is that from standard position or bearing?
Bearing, sorry, I should have said that. Yeah. All right, so let's do that too, assuming that this is also given as a bearing. So this is, oh, sorry, I should have labeled this. This is 290 miles per hour. So that we're considering that like the length of this vector, the magnitude, right? 290 miles per hour. That's the airplane vector. And in blue, how about the wind? Where's that one going to be? Where does the vector point? Into which quadrant? For this one, 300 degrees.
It would be the second quadrant.
Is that also second quadrant? 300. Yeah, sorry, it's also bearing. Sorry, it doesn't say that, but it should. I'm sorry. Well, we haven't gotten there yet. I just want to like picture these individually first, and then I'll worry about like how do we combine them. So the wind has this bearing, so 300 degrees is like 60 short of the whole way around. So I think maybe I'll draw it like that or something. I don't know. Maybe something like that. I'm gonna make it shorter too. None of this is perfectly to scale, but whatever. So 46 miles per hour. What's the angle there? 60 is the missing piece here plus 90. So okay, I'm with you. 150. Are you with us too? Yes, 150. So that's the blue angle there. In standard position is 150. Everyone cool with the bearing discussion? It's annoying is what it is. I acknowledge that. But do we at least understand it even though it's weird? If so, then that's good. Okay. Because it is annoying, I agree. I'd rather dispense with it too. But it's like a thing, so. What do you think the actual bearing, what do you think the actual course of the plane looks like then? The actual velocity of the plane. I mean, if we really do agree that these things add in each individual dimension, then together they should add in 2 dimensions too. And the resultant should be the sum of these 2 vectors, right? We had a way of picturing that yesterday. Unfortunately, I have to cut up into these words here, I think. I think it's going to look something like this, right? It looks like it's going to maybe be helped a little bit along by the wind, right? One way of visualizing this would be, like we said yesterday, to think about adding the plane and the wind end to end, yeah? So the blue is the wind, and that would result in this purple. And we discussed yesterday that vector addition is commutative. Does it work to also do wind plus airplane? Yeah, if we do blue plus red and add those end to end, we also end with the same purple vector here. Okay, so I think that's the picture I have in my mind of how the plane's gonna, what the velocity vector is gonna look like. I think it's gonna be going a little faster, and it's gonna be tilted off course by this much, by a little bit, right? Which both of those should make sense intuitively too. If the wind is blowing this way, kinda, seems like that should be about right. So let's actually run the numbers here. Write these in component form, each one, and then add them and see if we can come up with that purple vector. So airplane. How do we do this? 290 cosine 98. 290 sine deviate. .46 cosine. So far so good. And then add those, but when you do this, you're going to add component-wise, right? Add the x components, add the y components, and if you could, let me see if I can catch you before you actually do it. Can you store those values once you get them in A and in B on your calculator, please? Okay, so we can go ahead and do that. I'll do it too when we grab my calculator. Yeah.
So when you do those, you give out 290.6, but can you do, I mean, the cosine of 98 and 150, but can you do the angle measured in bearing or no?
You might be able to, but you have to interpret the picture we have is not the picture that you would have then, right? Because the cosine of the, you'd have to like really think hard about what picture you're drawing and what the cosine of your angle means. Because cosine and sine both assume, the definitions of cosine and sine assume an angle in standard position, right? So your picture would be a little weird, and you'd have to like think hard about what you're doing. All right, so like I said, I'm going to do these. I'm going to add the x components here and the y components. Store these values in A and B, please. And we'll come back together in a second here. Make sure your calculator's in degree mode. Did you get negative 80.2 approximately? I stored that in A. So and then 310 approximately. These are approximate. Okay. Again, store these if you will, please, in A and B. The full values of these, right? So know that as I move on in this problem, I'm using no rounded value at any point ever. Okay. So what is the actual velocity of the plane? I guess one way you could report the answer is in the purple vector components that I just gave, right? That would be one way, I guess. But if like you're an engineer and your boss asks you this question, you might like maybe give him, you know, he might be, if you said negative 80.2 comma 310, he'd be like, excuse me. Like maybe you want to give it back the way that it was given to you in bearing with a magnitude, right? So let's actually find the magnitude of this vector and see if we can go backwards on this here. Can we find the magnitude of this vector? Now that A and B are in your calculator stored, it's just what? Square root of A squared plus B squared. So hammer that in, and you'll have the exact values stored there. That's great. Alpha A squared plus alpha B squared. Okay. So I'm getting 320 approximately. Push the buttons too. Make sure you're getting the same thing I do. Help each other out with the button pushing. So 320 point, I mean that's 3 sig figs, but it's like 320.3777 approximately miles per hour. So are we helped along by this wind? We are actually going faster by quite a bit actually, right? What about the angle? How do we find the angle? It's a second quadrant angle. So what might you reach for? How would you do this? What buttons are you pushing? What might you do? The second quadrant angle. Any suggestions? Well, the actual velocity of the plane, I mean, you might give, velocity is like a vector, so you might give magnitude and direction. So theta, I might compute by doing what inverse trig function there? What might be a good choice? Yeah, I think cosine inverse is a good choice. I don't know. Actually, you can make an argument for other ones too. What would you have to type in then? Cosine inverse of what? Yeah, A, right, this thing, divided by on my calculator, I typed in ants, right? Because I had just done this calculation a second ago. Actually, I lied. I haven't done it yet, but here it is. Alpha A divided by answers. So because I had just typed this in, whatever. Or you can store this value and see if you like, whatever. But don't you ever use a rounded value, right? So I'm getting approximately 104 degrees in standard position, 0.5. Okay? That's not a bearing though, so if that's 104 degrees, which by the way, does that seem reasonable for that purple vector? Okay, it looks right, it looks about right. Let's just do a little reasonability check every time we have a chance. All right, great, and then what? And then what? How do we convert that to bearing again? So if this is 104 degrees, what's this? What would you do? What would you do, people of the crowd? If this big angle from here all the way to here is 104, excuse me, if this angle is 1/4, what is that big angle? How would you figure that out? Let's ask easier question. What's this angle then? If this is, the whole big angle is 104 degrees, say, then this is like 14 degrees. So how would we find the big angle? 360 minus that. No, don't use any rounded values. So what do we get? 320. Let's do 3 sig figs now. Miles per hour at, I just figured things by accident. Shoot, where'd it go? Here we go. I'll just do it again. Cosine inverse alpha A divided by. Yeah, 346 approximately. So 3 sig figs. So I might say the plane is going 320 miles per hour at 346 degrees from north, right? Is that cool? As a bearing, like I'm trying to make this clear. This is like a bearing from north. If you want standard position, we did that too. But there it is. Okay. So is that cool? Does that make sense? One other way to do this problem, by the way, is to conceptualize it this way. I don't want to do the whole problem again, but I just want to draw this quick picture. If here we have the airplane, and here we have the wind, and the vector we're looking for then is this vector, like we just drew a picture earlier, I think a lot of us also might look at this and be like, hey, that's a triangle. And you've studied a lot about triangles. And the other thing you know coming into this problem is the length of this side, if you want to say, of this triangle, and the length of this side of the triangle. And I think it wouldn't be very much work to compute that angle, given the angles that were given in the problem. And then if you know 2 sides and the included angle, can you find the third side? What might you use? Law of cosines, if you're like a lover of triangles, if you're a lover of law of cosines, this might be for you. So another way in on this problem would be to like conceive of it as a triangle and use previous tools, and that should generate the same length that we got for that vector. The other piece we still might want though is this angle, right? But that's not a problem because once you have this triangle in your grasp, you could find this little sliver of an angle, couldn't you? Right there. And you already know this angle because it was given. You could just add it. You could figure it out. So the point is, you could like also, instead of using component form, if you like take this new method, you could use triangles and some geometry and kind of like noodle your way into it, and you would probably get the same answer too. I think you should if you do everything correctly and you think clearly. You should get the same answers too. So I just want to make that approach available to you. That's not the approach I'll use up in front, and it's not the emphasis, but certainly any correct method is always welcome. You guys want to talk about llamas? I know I do. Okay. All right, so 2 cowboys are wrangling this llama. I guess we'll assume a coordinate system, though it's somewhat arbitrary, of this being kind of the x-axis that we drew here maybe. these are in standard position. The cowboys don't even know anything about bearing, so that's good. All right, so this is 21 degrees in standard position. You might actually call this angle maybe negative 17 degrees. If this is our coordinate system, we might call it that way. Again, let me just emphasize that the coordinate system is like a human construction we're laying on top of this that's arbitrary. You could actually rotate it however you like, and it would still work out fine on this problem. All right, you ready to add the vectors together?
Wait,
I think when we add them, we'll get like some vector, something like that. I might have actually, it's probably closer to the x-axis than I've drawn it, right? So if we add these two together, what do we get? 20 cosine 21, comma 20 sine 21. Plus 30 newtons times cosine of negative 17. 30 sine negative 17. What's a 17? But again, maybe store these in A and B on your calculator just like we were just doing. I'm getting down here 47.4 newtons, and over here something else. Negative 1 point, wait. So is it actually below the x-axis by a little bit? I really drew it wrong, didn't I? So it's negative 1.6. So it's actually, can you conceive of why my diagram might be wrong? I mean, I didn't draw it to scale. So it's actually a little below the x-axis. Negative 1.60 newtons. All right, I'm storing that in B. Okay. What's the magnitude? I'm getting, actually the 3 sig figs, I'm getting the same, I'm just getting the x component. The 3 sig figs, it's like the y component doesn't matter very much in this example, which is fair. I mean, it's quite a bit, it's really, there's not much of a y component. It's mostly horizontal, yes? Okay, and then we could actually find the angle too, but let's like pause for a second and actually read the question. What are we supposed to be doing? All right, so the llama is holding her ground. The cowboys are too. There's this epic battle going on. But if the llama is holding her ground, what must be true, physicists? If they're applying this force in this direction, this is the cowboy vector, then the llama, in order to stand still, is applying a force also in the
Opposite direction.
yeah, and then what's its magnitude? It's not just the opposite direction, it's also equal. Thank you, Isaac Newton. Yeah, all right, good. So yeah, it's applying, the llama, she's holding her ground by applying a force equal and opposite, right? So there is also like some friction to deal with, like there's maybe some more to talk about, but yeah. If she applies more force than they do, what happens? Yeah, she'll like move backwards, right? We're in static. We're like, we have this static situation where no one's moving. Yeah, okay.
What happens to the llama wasn't applying any force, and they were still applying that force, and the llama's still applying
Gravity.
the llama's gravity.
I didn't hear that question.
I was saying, like, what if the llama's not using the resistance?
Yeah, what if it's just really bad?
Oh, she's just really heavy. Yeah, she is then. It's just that there's a force that's due to gravity together with the ground, right? Providing some friction. Those two things combined. I'll leave that to a physics class. But the only thing we cared about though is the magnitude of the resistive force, which is the same as the magnitude of the cowboy. So I think we can just box that as our answer. let me just, without even writing, just say how you might approach this, because I think there's one in the homework. Can you deal with 3 forces? These are all in standard position. How are you going to do it? Write out component form for each one. Do you see the way in on this? Right? Can you do this with lots and lots of forces? Absolutely. Nobody cares though, so I'm not hurt, it's okay.